So we're going to kind of go through these examples as a way to teach it, because really it's just the best way to throw a bunch of examples at you and show you all the idiosyncrasies of these kinds of problems as we move along. So the first problem, you may read something, you may read a problem, or may be told that somebody's at the top of a cliff or top of a building or somewhere up higher, and they're 10 meters above a lower point. In this case, I'm going to say, well, let's be 10 meters above a lake or a river. You're on a cliff, and you're going to drop an object. It could be a ball, it could be a rock, it could be a penny, it could be whatever you're dropping, all right? And in the problem, all it may state is, you're 10 meters high, you drop the object from rest. How much time does it take to hit the lower point? How much time does it take to get to the river? So you're only given very little information. You're given the 10 meters. You're given that you have that you drop it from rest, and that phrase is very important. You drop the object from rest. That means when you let this go, you just let it go. You don't give it any upward push. You don't give it downward push. You don't give it sideways push. You just drop it, and it falls straight down. Right? So from rest. Now, that's important because if we know, one, that it's going to fall, and we know the acceleration is going to be 9.81. We're assuming that this is on Earth. It didn't say otherwise. The problem doesn't say otherwise. So if the problem doesn't say otherwise, you're on Earth, and you're going to assume that there's no friction due to the air. There's no air resistance. Nothing's going to hold up the motion as it falls. Okay? So if it's on Earth, we know the acceleration is 9.81 meters per second squared. The question is, positive or negative? Well, there's a couple ways to interpret this, but I'm going to tell you for just the ease of doing these for the rest of the year, conventionally, we say that upwards is positive x. Or positive x, sorry. X is that way. Positive y. So we're going to say that upwards is positive y. Now, in other problems, previously we were talking about x, positive and negative. Something was traveling on the x direction. Well, here in free fall, we're going to travel in the y direction, and that's okay. It's still along a line. We're still linear motion. So instead of calling things x, we call it y for displacement. No big deal. Just, it's a different letter, but it still means displacement. And so if we make positive upward, but this object is going to fall and speed up as it falls. Because remember, free fall, you start from rest and then it gets faster and faster and faster and faster and faster. As a matter of fact, it changes speed, or velocity, almost 10 meters a second per second. That means the first second to the second to the third second, it's going to gain 10 meters a second, then the 20 meters per second, then the 30 meters per second. It's going to get faster and faster and faster as it approaches the ground. So since we called positive upward, the acceleration is going to be a negative because I'm speeding up downward. That's also going to affect our delta y. What was our change in displacement? Well, it went from here to here. I did change displacement. I changed 10 meters. But it was downward because I started here and ended up here. And so our initial position here, our final position here, that means I went downward 10 meters. That better be negative. So we know that. Okay. Now, a lot of problems, again, backtrack, a lot of problems won't tell you the acceleration. they won't list it in the problem. But if it's an object falling or thrown upward, yes, upward too, because when you throw something upward, it's then going to immediately try to fall downward. So if anything is in this free fall kind of situation, the problem doesn't have to tell you 9.81 because you're supposed to know that. You're supposed to apply that appropriately. Okay, we fell 10 meters, that has to be a negative. If I release this from rest, and in the previous videos and the previous lessons, I said be very careful. If it says it starts at rest, it means it had no velocity when it was let go. No, there is no plus or minus on that because it's not moving at all. And so if I know the object starts up here, and I put x's, but like I said, oopsie, x's and y's, it's just a letter, it's going to move along that line, so that should be y's rather than x's to be consistent. How much time did it take? Well, now all we have to do is go back to those 4 acceleration formulas and figure it out. That's all we have to do. So, if you go and pick the right formula, probably this one. That one will work. But you got to be careful with the signs. Gotta be careful with those signs. And this goes away because it's times 0. And you're going to end up with negative 10.0 divided by negative 4.905 equals t squared. Now, what's important here is, I know I have negatives, but they're going to make a positive. Negative over negative makes positive, because then I got to take the square root to find the time. When you do this, and if you're finding time, it had better be you had better be taking the square root of a positive number. If you get a negative here, you use a wrong sign somewhere, and you better go backtrack and try to find out where you made your error. Okay. And so you're going to get that answer. And hold on. 2.04. seconds. And then if I take the square root of that, 1.43. Right? So that's the one problem. I'm going to come back and do another problem.